delegates to the third lecture session of Popular Lecture Series 2021-2022 sponsored by Soft Material Research Society Jaipur, organized by School of Applied Sciences and Center for Renewable Energy and Storage, Suresh Gambihar University, Jaipur. I heartily welcome our keynote speaker of today's session, Dr. Vaibhav Kulshrestha, Principal Scientist, CSIR-Centre Salt and Marine Chemical Research Institute, Bhavnagar, Gujarat, India. Welcome, sir. Taking the
Thank
session
you.
ahead, I would like uh, I would like to take this opportunity to briefly introduce our speaker to all the participants. Dr. Vaibhav is presently working as Principal Scientist, Membrane Science and Separation Technology Division in CSIR Centre Salt and Marine Chemical Research Institute, Bhavnagar, Gujarat. He received his PhD degree from University of Rajasthan, Jaipur. He has received many prestigious awards or fellowships like D.S. Kothari Postdoc Fellowship, BST Max Planck Visiting Fellowship, ICTP Associateship from International Centre for Theoretical Physics, Italy. He is a recipient of Young Scientist Award from Council of Science and Technology, Lucknow. He has undertaken many research projects from various funding agencies such as CSIR, DAE, DRNS, ONGC, OECD, and DST. He has 2 international patents and more than 125 research publications to his credit in the journals of international review. He has also authored many books and book chapters and also contributed significantly in many national and international conferences. Today, Dr. Vaibhav would be talking about functional membranes, a tool for environment and energy. So, without taking much of the time, I would like to invite Dr. Vaibhav to take the session ahead. Over to you, sir.
Thank you, Dr. Neha, for the nice introduction. First of all, I would like to thanks to the convener, Professor Gaurav and Professor Jain. Thank you very much, Professor Gaurav and Professor Jain. So, namaskar to all of you. Just a moment. So, title of today's presentation is Functional Membrane, a tool for environment and energy. So here I will discuss about the different type of membranes for basically for environment and energy application like water purification, other industrial application, and energy application like fuel cell, redox flow batteries, reverse electrodialysis, and water splitting. So before come to the presentation, I would like to introduce my institute. So we are the CSIR laboratory and situated at the sea coast, you can see here. And the name of the institute is Central Salt and Marine Chemical Institute. So institute is working for the different aspects of seawater for marine chemicals. Here you can see we are working. Here you can see that we are working for salt preparation, salinity gradient, corrosion. We are also working for different material. Different. Yes.
Slide change नहीं हो रहा है.
Oh. So now.
नहीं. No.
Sir, please go to full screen.
Yeah, it's full screen now. Just a moment. I'll check again. Yeah, now can you see it on full screen or not?
Sir, only the front slide is displaying functional membranes, a tool for environment and energy.
So is it in full screen?
No, no.
No, it is not
Sir,
full
you
screen, sir.
share it again. With
Okay,
all-
okay.
Try to choose option entire screen. I think that is better.
Okay, okay. So it's the entire screen. So I'm not able to share it. I don't know why, but share option is not available here. That's why I'm choosing a window. Uh, so now is it full screen or not?
Sir, it is not full screen, but the slides are visible.
About what about now? It's changed to
No,
second
it is
slide.
not. No, it is not changing, sir.
Just a moment. I call someone.
So while presenting, you can select the entire screen, then perhaps it will go ahead. You might be
Actually,
selecting a single window.
Actually, I am trying to share his entire screen, but I'm not able to share it. The share option is not okay. I think now. So now you can see the slide.
Yes, sir. Try to change
Yes, sir.
X1.
Uh, so it's changed.
Yes, sir.
Yes, sir.
Working perfectly fine.
Okay, okay. So now I start again it. So we are working with the different aspects of seawater and chemicals. So here you can see we are working for the salt preparation, bittern-based specialty materials and fertilizer. Obviously, we are working for the material science, catalysis. For seawater, for in the field of water, we are working for the water purification, desalination, and membrane technology. And I am working in this area only. We are also working for the salinity, corrosion, wasteland research, and obviously we are working for the marine biotechnology and ecology. So I first cover the energy and environment scenario. Here you can see in India shares a global energy demand to rise to 9% by 2030. So here you can see I took this picture from the internet. It's available. So by 2035 we need 9% extra energy, and here in India coal will remain the dominant fuel produced in India with a 65% of share of total production by 2035. Renewable overtakes oil, is the second largest, increases 4% by 2035 and will reach around 14%. So here you can see the mode of crisis. Now we are suffering from the corona since last 2 years. It might be we might be suffer from energy, air or water by 2050. So it gives a lesson that we ready and prevent the forthcoming global issues. So the remedies is we need the materials which can not only produce energy but also can store the energy as well as environment friendly. We also need the process which can desalinate the water by different means. So this picture shows the water scarcity in India. You can see more than 54% of India faces high to extreme high water conditions. Rajasthan, Punjab, Gujarat, Delhi, Haryana, in fact, Jammu, Kashmir, and some other states is also suffering with the same problem. So most of the places we are getting problem associated with water. It may be salt, and some other ions like fluoride, arsenic. Rajasthan is also suffering from the from both arsenic and fluoride. In Gujarat, we are also facing the problem of arsenic and fluoride. So there is the solution to get rid of by this problem. You all know about that the only 1% of fresh water is available in the world, and 90% water is the salted water, and we get the 2% of water from the icebergs. So there are the so most of the water is not the potable water. So total we depends only on the 1% of fresh water, where we consume 21% for ourselves, 10% goes to the industries, and 69% goes to the agriculture, for agriculture. So the only way to reuse is the only way to recover this water. So we can, and desalination is the another way where the salt water can be desalinated. So there are the different water treatment technology are available. You can see in India there are two type of city: class 1 city and class 2 city, where the population is higher than 1 lakh and less than 1 lakh. You can see here 498 cities are in the class 1 cities and 410 cities in the class 2 cities. And from this third table, with combined class 1 and class 2 cities, sorry, you can see the sewage generation is around 38,254 gallon, where we are able to treat only 11,786 of the water. So around 70% of water is going in the west and is just creating the problem for environment. So the solution is the zero liquid discharge. So this is the only solution where we can discharge we can treat our whole water. So here here you can see membrane is the technology where we can get our water back by different means. Here you can see first is the physico-chemical pre-treatment of that sewage water, then biological treatment via different bacteria which can degrade the bacteria and microorganisms which can degrade the pollution, then goes to the membrane filtration. Here membrane filtration comes in picture. These are the different type of membranes. It may be RO membrane, NF, UF membrane. Then finally we can get we can evaporate and concentrate this water to our use. So from last slide, here you can see the membrane filtration. So I just come to the membrane. So what is the membrane? So membrane is a thin selective barrier which allows the preferential transport of solute. Membrane can separate particles and molecules and over a wide particle size range and molecular weight. Here you can see in our daily life we are using different type of membranes. In fact, nature is also gives different membranes. Kidney is so the main natural membrane is the kidney membrane we use. So here, why membrane technology? So here in the membrane technology, no chemical required, highest quality of water we get from the membrane. These are the versatile, cost is low. In fact, energy consumption is the main drawback for these membranes. Accordingly, membrane can be classified in different categories by different means: structure and morphology. Membrane materials, it may be polymer, zeolite, or coal, or different type of charcoals. And selective barrier, porous, it may be porous, non-porous, charged, or with a special chemical affinity. So according to morphology and configuration, membrane can be divided in different category: polymer, ceramic, glass, metal, and liquid. in fact, the structure is also different. It may be symmetric or asymmetric. Symmetric means a homogeneous type of membrane with which may be a dense membrane, or a sponge type of membrane, or porous membrane like cylindrical pores, which can be generated by ion irradiation or subsequent etching. In the term of asymmetric membrane, it's a different. There are different asymmetric membrane available in market also. So on a porous structure, we cast a layer, porous skin layer, a homogeneous skin layer, or homogeneous skin layer, a TFC type membrane, thin film composite type membrane. According to these membrane can be configured in different type of infrastructure, like flat sheet type, spiral bound type. In spiral bound, a large volume of membrane can be bound in a spiral form. Tubular membrane, capillary type of membrane. Basically, these capillary type of the membrane are the hollow fiber membrane, which used in for the ultrafiltration or microfiltration. So classification of membrane according to the pores, you can see here. We started from the 0.01 nanometer to 100 micron. So here 100 micron membrane means it's a microporous membrane where we can remove our pollens, yeast, bacteria, and colloids can be removed by this membrane. Then organic molecule in the range of from a few micron to few nanometer can be removed by other second type of membrane, which is the microfiltration or ultrafiltration membrane. Third is the nanofiltration membrane, by which we can remove the a few amount of dissolved solids, and organic compound can be removed. Other membrane is the RO membrane, which is a dense membrane, by which we can remove all total dissolved solids. So now I come to the water purification. For membrane topology for water purification, here you can see we can get different type of water by the different type of membrane systems. From here you can see seawater desalination can be done with the TFC seawater RO membrane, and high pressure is required here. Another is the brackish water desalination, where medium pressure is required, and TFC means thin film composite brackish water membrane is used. This 4040 and 8040 is just the module size. 4040 is the 4-inch module, and 8040 is the 8-inch module, by which we can get the potable water. And this type of membrane can used from few thousand ppm to the 10,000 ppm of saline water. Third one is the nanofiltration membrane, where module is a spiral bound module, and here only low pressure is used. So where the TDS is not very high, is around, it's up to the few hundred, means up to the 1600, we can use this nanofiltration membrane. It partially remove the TDS. TDS means means total dissolved solid present in the water, like main constituent of water is the sodium chloride. So we use the nanofiltration membrane for this type of water. Another is the microfiltration membrane, where we use the hollow fiber technology or ultrafiltration type of membrane. So this is the municipal water, we get it from our tape. So here only we can use a microfiltration type of system. Another is the ultra pure water, which is used for the specific applications to get the deionized water. It is high resistance water, where the resistivity is 18.2 mega ohm. So for this we get a electrodeionization system. Another type of membrane is the ion exchange membrane, which is also used for water application, water desalination, purification, and some other applications. So these ion exchange membranes are the basically charge membrane or functional charge membranes. So these are the different driving force for the different type of separation processes. You can see microfiltration, ultrafiltration, nanofiltration, reverse osmosis, and for pervaporation, the gradient or driving force is the pressure. Electrical is the driving force for this electrodialysis and electroosmosis. Concentration for dialysis and osmosis, sorry, and temperature is the gradient for the thermoosmosis. You can see the pictorial view of different driving force here also. So now I come to the ion exchange membrane, which are the functional membrane. So ion exchange membranes are the basically carries positive and negative charge and allow the exchange of ions, and can be classified into the two category. One is the cation exchange membrane. These membrane containing negative charge and allow the exchange of cations, and another is the anion exchange membranes. These membranes containing the positive charge and allow the exchange of the anions only. So these are the different type of membrane where the gradient is the potential, and these membranes are not allowed the passage of water. These membranes allow on the passage of ions only. So again, this is the classification of ion based on the charge functionalities. So for the cation exchange membrane, the functional group it may be sulfonating group, phosphorylating or carboxylating. Basically, we use sulfonation for these membrane, which is very strong. For anion exchange membrane, this tertiary amine is used as a functional group in this type of membrane. Another quaternary and primary amine is also used for anion exchange membrane, which is easily dissociable. Another type of membrane are the amphotic ion exchange membrane. Basically, amphotic ion exchange membranes are nothing. It's the combination of cation and anion exchange membrane, where the both of the functional group are present in the membrane matrix. So these membranes are permeable for the both of the ions, but there are different application of amphotic ion exchange membranes also. So these are the basic properties which should have with the ion exchange membrane. It's high Perm selectivity means they should allow only one type of ion, means only positive or negative ion. Transport number for these ions should also be higher. Ionic conductivity is the main component for any membrane. The membrane should be highly conducting and should store the optimum water, should not store high quantity of water, otherwise it will lose its stability. Lowest possible electroosmotic drag, water should not pass through the membrane. It should be highly chemical and oxidative stable. Membrane should be fouling resistant, and homogeneous phase morphology is good for any membrane. So this is the historic timeline event in the development of ion exchange membrane. So first electromembrane process was started in 1819. Earlier we used a ion exchange membrane. In 1918, first ion exchange membrane was developed. It was the Nephron membrane. Bipolar membrane was also introduced at the same time. So from 1980 to 2000, different types of membrane has been developed, but not actually commercialized. So up to now, in market, only Nephron membrane is available as a benchmark, which was developed in 1980. So many researchers are working for these ion exchange membrane development, not only for water, also for the energy applications. So there are the different application of ion exchange membranes where our group is working with the fuel cell, where proton exchange membrane is used. Redox flow battery. Here, this picture is for the vanadium redox flow battery. Here, both type, in fact, all three types of membrane is used. It may be acidic, alkaline, or amphotic ion exchange membranes. Electrodialysis, basically electrodialysis by electrodialysis, we can remove charge from any organic, or it's also used for removing of salt from any solution. Ionic metathesis is also a type of electrodialysis where a 4-compartment cell is used, which is used for exchange of ions. Another application is the diffusion dialysis, where alkaline anion exchange membrane is used, and we can reclaim the waste acid by a mixture of acid or metals by this process. So it's again the elaboration of different types of different application of ion exchange membranes, like dialysis, diffusion or donor dialysis, water splitting. For water splitting, it's also used in the energy generation by water splitting. For hydrogen generation, bipolar membrane is also used for water splitting in the form of hydrogen, and also used for chloralkali generation by the industries. Polymer electrolyte is used in different energy application, like solid polymer electrolyte for fuel cell and redox flow batteries. Main application is the electrodialysis, where we can desalinate the water. It may be a brackish water or seawater. We can also get ultra pure water by a combination of absorption and electrodialysis, means it's the electrodeionization process to get the ultra pure water. It's also used for the waste management, means recovery of inorganic, recovery of waste acid, separation of organic and inorganic. Electrodialysis is also used in the food and biotechnology for demineralization and de-acidification of the fruit juice, purification of fermentation products. So versatility of ion exchange membrane in the benefit of bird is that here you can see a picture where all type of energy is used. So electric lines, hydrogen piping, CO2 piping, and natural gas are used. And from here you can see where we are using the ion exchange membrane in electrolyzer. In fact, short-term energy storage, means in redox flow battery, we also use the ion exchange membrane. Fuel cell, we use ion exchange membrane. Electrolyzer, we use ion exchange membrane. And in hydrogen fueled vehicle, we also use the ion exchange membrane in the form of alkaline ion exchange membrane or proton exchange membrane. So it is no doubt that ion exchange membrane are renowned for energy and environment application. After declaring by our respected Prime Minister for the hydrogen mission, many big companies are trying to produce the proton exchange membrane. So this is the domain morphology of well-reported Nafion membrane and hydrocarbon-based ion exchange membrane. Basically, hydrophilic and hydrophobic domains plays critical role in ion conduction in any membrane and formation of optimum hydration environment for electromembrane application. So it's just the picture of Nafion 212. The basic structure for Nafion 212 and 117 is almost same. So basically Nafion is the benchmark membrane, and the quality of this membrane is wide and more separated channel to allow the passage of ion across this. The membrane is less branch. Ionic conductivity is very good. Membrane is very stable in terms of mechanical. The functional group present in this membrane is the basically sulfonic group is present. And another picture is the sulfonated polyether ketone. Basically, is the hydrocarbon-based membrane. So here the channel present in this membrane is the narrow channel, which are less separated. The membrane is highly branched, and that end conductivity is produced here. And obviously, large number of functional group is present here, but the membrane is not as per the Nafion. Because in Nafion is the basically PV is a fluorinated backbone membrane, which gives it extra mechanical stability. So transport mechanism in membrane takes place by different types of mechanism. It's the Grotus mechanism, another is the diffusion and migration, and the conventional method. Grotus means a hopping type of mechanism where a ion passes through the presence of functional group from one to another, and another is the side hopping mechanism, and final is the vacuolar type mechanism. So it's just the little bit of research work I'm showing here. Is the synthesis of polyethylene and methylstyrene based ion exchange membrane. So basically here you can see it's the chemical structure of polymethylated styrene and divinyl benzene, where we are taking the polymerization. It's the radical polymerization in presence of polyethylene, reliant base, high density polyethylene and linear low density polyethylene is used. So first we prepare the polymer by using polyethylene, styrene and divinyl benzene. Then we process this polymer and we convert this polymer into a thin film of around 200 micron. Then in the last step, we functionalize these membranes by the sulfonic acid to presence in the sulfonic acid group by the chlorosulfonic acid. To prepare the alkaline anion exchange membrane, first we do the benzyl bromination in presence of N-bromosuccinamide, then quaternize the membrane by tertiary amine. So these are the pictures of anion exchange membranes and cation exchange membrane, and it is in the large scale production. We are doing the large scale production for ion exchange membrane, and India, we are the only organization which is working for the large scale development of the ion exchange membrane. So this table shows the property of our interpolymer type ion exchange membranes for both anion and cation exchange membrane. So aerial resistance is around 2 to 4 for anion exchange membrane, which is 1.5 to 3 for cation exchange membrane. Selectivity is more than 90% for both type of membrane. Water content is optimum. It's neither low nor high, and ion exchange capacity is around 1 milliequivalent per gram. So our membranes are comparable to the membrane available in the international market. In fact, for the comparison of cation exchange membrane, we compare our membrane with the Nafion 1171. So all the properties are similar. The only drawback with our membrane is the thermal stability. Actually, here we are using polyethylene as the binder. So polyethylene, we cannot go above the 50 degrees centigrade. After 50 degrees centigrade, polyethylene get loosed and ion goes and water passes across the membrane. So this is just the FTIR. This is the FTIR spectra for both of the membranes. So presence of sulfonic acid group and quaternary ammonium group can be seen here. So there are, as I earlier told you that there are different application of ion exchange membrane. So first is the electrolysis. In this picture, you can see is the representation of electrolysis setup, where we are using the NaCl solution as a feed, and we are here you can see there are the basically two channels. One is for the diluted stream, another is for the concentrated stream. So by this we can desalinate our water, and we can get potable water of less than 500 ppm as per BIS norms. So here electromembrane process is the potential driven membrane interface application for separation and purification of salt, acid, alkaline solution. The operational parameter for this electrodialysis is the basically current efficiency of ED unit. Power consumption for desalination is less than 1 kilowatt hour per kg, and almost 99% of salt can be removed by this. There are different application of electrodialysis, water desalination, resource recovery, reverse electrodialysis, and concentration of waste acid and alkaline solution by metathesis electrodialysis. So by this, on the basis of this electrodialysis, we installed a plant in the rural mission near our laboratory. It's around 20 kilometers from here, where the fresh water is not available for the blazers. Here we install a plant with a capacity of 1000 LPH, and this plant is working since 4-5 years, and it's able for a blaze where we are not using electrical power. The plant is based on totally solar powered. So another application for environment is the metathesis electrodialysis. In the metathesis electrodialysis, you can see here we are using the four channels, and it's the just a reaction scheme. You can see here A plus X minus plus B plus Y minus. We can change A X Y by and Y by X by this electrodialysis, and here we can convert our low value salt to the high value salt. The advantage of this system is the purity of co-ion inclusion percentage in obtained product is very good, and the system is same as the electrodialysis. So by this we can purify our salt. Value added chloride free fertilizer can be produced. For this, we are working for the effective recovery of chemicals and water from byproduct ammonium nitrate solution. This work is assigned by the BARC, and huge amount of ammonium nitrate generate while uranium processing. So this ammonium nitrate solution, they don't have idea how to use this ammonium nitrate byproduct. So they give us a project to convert this ammonium nitrate byproduct by some value added product. So here we are using KCl and ammonium nitrate as a feed, and we converting this ammonium nitrate to the potassium nitrate, which is a fertilizer, and India totally depends on export for the potassium rich fertilizer. So here we are utilizing both low value potassium chloride to the high value potassium nitrate, and this ammonium nitrate is converted to the ammonium chloride, which can also be used. So these are the few data. You can see we are able to here you can see we are able to convert 90% of potassium chloride into potassium nitrate, where the purity is very high. It's around 97.67%, with the very low energy consumption, which is around 0.5 kilowatt hour per kg of production of KNO3, and energy efficiency is little bit low, around 52%. So we are trying to improve the system and optimizing the parameter to improve the energy efficiency of this system. So another is the environment diffusion dialysis. Diffusion dialysis basically used for the recovery of waste acid, where the some ions are also produced. Some ions are also present. So it's the energy efficient process which is generally used to recover essential chemicals from industrial effluent of very high TDS concentration, and also used for acid enrichment. So the main application of this type of system is the heavy metal ion removal from wastewater. In fact, acid recovery also, acid and alkali effluent purification. So it's just a small system where we are using or purifying or recovering the acid and metal salt. The effective area here we are using the 80 centimeter square, and the compartment volume of the compartment is around 5 liter. So by this, here we are using polyphenylene oxide type of anion exchange membrane, and we perform these experiments with different acid like HCl, HNO3 and H2SO4 in the presence of iron sulfate, iron nitrate and iron chloride. And here we are using to recover the 50% of acid without without the iron. So this 50% of acid means almost 100% of acid. From here you can see this here basically it's working on the concentration gradient. So when the concentration of both the compartment get equal, then there will be no migration of the ions. So by this process, almost 50% of acid can be reclaimed in a single pass, or 100% of acid can be reclaimed by changing the solution of the product side. This is the another process, which is the electrodeionization for the production of ultra pure water. So ultra pure water is basically used for the semiconductor industries, all pharmaceutical industries. So here is the first step where we are using a pre-treatment and RO module. The product water passes through a UV chamber. Then here it comes a EDI module. Then it's again come in a UV lamp, a long wavelength lamp, where all the pathogens and all presence of microorganisms get dead. Then it passes through a deionization cartridge and finally stored in a tank. The resistivity of this water is 18.2 mega ohm, which is a type 1 of ultra pure water. It's just the pictorial representation of the system where a mixed bed ion exchange resin is filled between the anion and cation exchange membrane, and its continuous get charged. So these are the specification of ultra pure water developed by us, and comparison with the molecule water, which is very costly. It's around 20 lakh rupees. So product means water quality is almost equal. We supplied the different EDI unit at different laboratories and also patented this system. Now we are able to produce up to 100 LPH of EDI water. So these are the other application of ion exchange membrane. Is the chlor-alkali production where the ion exchange membrane used. And another is the capacitive deionization. So in capacitive deionization, our water passes through the cation and anion exchange membrane. A porous carbon type electrode is used, which trap these ions just before the current collector, and we get the desalinated white water by this. This is the membrane capacitive deionization. Sorry. Another is the bipolar membrane, which is also a very special type of membrane, special type of layered membrane, where both cation and anion exchange membranes are basically interacted with each other. An interfacial layer is also used here. So here you can see the different process for the preparation of different type of membrane. Is the loose laminating. Hot pressing is also used, where we prepare two types of membrane, and we stick these membranes with a binder. Casting on a membrane is the another method to produce the bipolar membrane. Co-extrusion is also a method to prepare the bipolar membrane. Then electro spinning is also a method for the production of bipolar membrane. So the advantage of this membrane is that unlike the water splitting during electrolysis, no gases are formed as a side product in bipolar membrane. This type of bipolar membrane used for the acid and alkali from the corresponding salt solution, and the BPM is also used for the energy application for hydrogen production. So there are the different problems associated with the bipolar membrane. Delaminating of the both the layer is the common problem. So thermal stability when the temperature increases above the 30 and 40 degree centigrade, membrane delaminated. And chemical stability, basically for the alkaline exchange membrane is the problem. So we are trying to improve the bipolar membranes. It's just a representation of what one membrane we prepare. Basically, here we use the commercial anion exchange heterogeneous type of membrane, and here we are using sulfonated polyether sulfone as a cation exchange layer, and a interfacial layer MOS2 is used. So the advantage of MOS2 used as the interfacial layer is a non-noble metal hydrogen evaluation reaction catalyst with higher water dissociation efficiency, and over potential is minus 191. So here you can see the physicochemical parameters is very good for this bipolar membrane. Here one can see the both of the layer of this below is the anion exchange layer and above is the cation exchange layer. We also performed the elemental analysis of these membranes to confirm the presence of MOS2. Here the principle is given of the bipolar membrane. When we used any salt, we can convert into the respective acid and alkali by the water, because at the interface of bipolar membrane, water splitting get place. So H plus and OH minus we get if we are using NaCl here. So one can get the NaOH in the one compartment, and HCl is the another compartment. So industries use this bipolar membrane for chloralkali production because here energy consumption is low. So in India, no one is producing the bipolar membrane. In fact, the cost of bipolar membrane in international market is very high, around 50,000 per square feet. So we developed this membrane, and it is in patent stage now. So the membranes are stable since last 2 years. There is no delamination. We are also trying to get some asymmetric type of bipolar membrane where we are using different thickness of anion exchange layer, because you all know that the migration of H plus ion is comparably higher than the OH ion. So it's around 2 to 8 times higher than the proton. So we are trying to reduce the thickness of an anion exchange membrane so we can get the more efficiency. We are also trying to change the interfacial layer to improve the efficiency of this system. So now I come to the energy application. Time is less now. So high power density device for energy generation is required. So ion exchange membranes is used in all three processes for energy production, energy utilization, and energy storage. In fuel cell, we get the energy in fuel cell and reverse electrodialysis. Water electrolyzer is used to produce the hydrogen, and flow batteries for the storage of the energy in the grid scale. So one of chief component which require a rational development in these devices is the ion exchange membranes. So it's just the basic principle of fuel cell. Basically, this fuel cell converts the chemical energy to the electricity by using a fuel which may be a hydrogen, methanol, or other. So here we are using the proton exchange membrane. One can see when hydrogen passes through this membrane, electron is generated, and we get it's complete the circuit, and we get the energy. The electrode direction you can see here. So on anode, H2 is divided into 2 proton and 2 electron, which combines here at cathode and generate the water. So here it is the zero pollution system. So the operational parameter to be assessed in fuel cell is the power density of fuel cell, hydrogen permeation, influence of carbon dioxide on ion exchange membrane performance. Obviously, stability is the main parameter, and lifetime and analysis of these membranes. So here we are using the proton exchange membrane. Another is the alkaline exchange membrane fuel cell. Here reactions are little bit different than this hydrogen. Then 2OH is generated with this alkaline exchange membrane. This hydroxyl ion pass from here to here, and we get the circuit completed. So basically, in fuel cell there are three important component. One is the membrane, another is the catalyst, and the electrode. So we are working for both membrane and catalyst. These are the few results with the methanol fuel cell. So by methanol fuel cell, here we prepare a composite with molybdenum sulfide with the sulfonated polyether ether ketone. Here one can see by the intercalation of 5% of molybdenum sulfide, the conductivity, the proton conductivity is of membrane goes around double from 30 to 80 degrees centigrade, and these are the half DMFC polarization study with the SPS membrane and composite membrane with the half cell. So with the composite membrane or with 5% of MOS2, we are getting around 60 milliwatt per centimeter square of power density, while for the virgin membrane we are getting just the 30 milliwatt per centimeter square of power density. We also prepare one more composite with the sulfonated boron nitride with proton exchange membrane and compare these membranes with the Nafion. So our membranes are superior in terms of the this power density, where we can achieve around 120 milliwatt per centimeter square of power density, where in case of Nafion 117, which is a benchmark membrane, we could get around 88 milliwatt per centimeter square of power density. Water electrolysis, you all know about the water electrolysis. It's just the journal about the water electrolysis. So these are the half cell reaction where hydrogen, where the water dissociated in the hydrogen and OH ions and get the electricity. So we just improve this water electrolysis with the membrane water electrolysis. The main advantage of the membrane water electrolysis is the selective modulation of ions towards corresponding electrodes. High purity of hydrogen is generated here. Reduce over potential for overall electrolysis process, afford operation at higher current density. So it's just the schematic representation of both type of polymer electrolyte water electrolysis, where we are using the proton exchange membrane. You can see here water is dissociated here, and finally we are getting the hydrogen and electricity. Another representation is for the alkaline water electrolysis system, where we are using a alkaline anion exchange membrane and get the hydrogen. So this is the another application of ion exchange membrane, which is the reverse electrodialysis. It's the schematic representation of electrodialysis, where we are using the external power source to remove these ions. But in the case of reverse electrodialysis, it's just the reverse of electrodialysis, where we are using the water of different concentration with the help of different concentration of water in respective channels. We are able to generate the energy, and we have a system by which we can generate around 100 watt of energy. Redox flow battery is another type of devices for energy energy storage. So different type of redox flow battery is used in the iron-based redox flow battery, zinc iodide or zinc bromide based redox flow batteries, and is the hydroquinone based redox flow battery. These are the common organic couple which is used, redox couple which is used to run this type of batteries. Here is the comparison of the redox flow battery with the lithium ion battery. So here we compare the lithium ion battery with the vanadium. So here you can see the number of cycles which can run the vanadium battery is much more higher than the lithium. Low self discharge is where, so we can it's possible here. Low environmental footprint with vanadium is also an advantage. Highly expandable, generates low level of heat, where the lithium battery we use in our mobiles on laptop gets heated. Charge and discharges simultaneously takes place here, can release energy instantly, suitable for connection to power grid. So vanadium redox flow battery can be suitable to directly connected to the grid and is the small footprints. So it's just about the vanadium redox flow battery. Why vanadium redox flow battery? So processable electrolyte is available here, and vanadium is available in all 2, 3, 4, and 5 states. Higher power density we get with this. No redox couple consumption by organic decomposition, room temperature operation, and high overall throughput. Theoretically, the life of these membranes, the life of these vanadium redox flow battery is infinite. So main problem associated with the vanadium redox flow battery is also a membrane, because only Nephon 117 is available till now as a proton exchange membrane, which is used. So this type of batteries is not in commercial level is available. It's on the lab level system is available. So these are the few data we generate with the vanadium redox flow battery with the help of fluorinated backbone cation exchange membrane. So we are able to generate around 89% of Coulombic efficiency with around 85% of voltage efficiency, which is almost comparable with the benchmark Nephon 117. Here you can see the vanadium permeability is also comparable with the reported membranes. It's the same here, the polarization curve with the power density we can generate around 350 milliwatt per centimeter square of power with 100 milliampere per centimeter square of around 400 milliampere per centimeter square. So from this graph you can see the performance of our membrane is almost, in fact, better than the Nephon 117. The disadvantage of Nephon 117, one of the disadvantages is that it does not work above the 80 degrees centigrade. So it's all about the water and energy application. These are the facility available with the institute, FTNMR, FIR, all the major facilities like TM, SEM, all thermal analysis, XPS, mechanical analysis is available in the institute. Institute welcome the collaboration. In fact, institute also welcome for the dissertation of undergraduate and postgraduate students. So I would like to acknowledge Council of Scientific and Industrial Research, which is my parent organization, funding agency, SERB, DIBRNS and UGC, DAE, CSIR. Obviously, without team members, it could not be possible. So thank you.
Thank you so much, sir, for such an interesting session. Sir, I can see a few questions
Yes.
in the chat box. If you allow me, I can ask.
Yeah. Sure.
Yeah. So the first question is from Dr. Lokesh. What defines the stability of the membrane in high salinity conditions?
For salinity, mechanical stability of the membrane should be higher. In fact, when we are using it in the water, then there is no need of chemical stability. So mechanical stability should be there.
Okay, sir. So moving to the next question. This is from Preeti Sharma. What is the reason behind the color of CEM and AEM, brown and silver color respectively?
Actually, the base material is different for
लाइट इन
both
डालना
of.
उसमें क्या आप क्या कन्वर्ट कर रहे हो मैकेनिकल एनर्जी इनटू इलेक्ट्रिकल एनर्जी
All the participants are requested to mute themselves. Thank you. So you may please proceed.
Actually, here we are using different type of base materials, and for CEM we are using a highly corrosive environment. Chlorosulfonic acid is used for the functionalization of cation exchange membrane. That's why it gets darker. And benzyl bromination is used for the preparation of anion exchange membrane, which doesn't provide any color.
Okay, sir. I hope the query of the participant is solved. Moving to the next question. This is from Dr. Kriti Srivastava. How ion exchange membranes can contribute for sustainable energy conversion?
For energy conversion, you can see here, ion exchange membrane an ion exchange membrane is used in the membrane water electrolysis, by which we can produce the hydrogen. In fact, polymer electrolyte fuel cell, we use the ion exchange membrane. For alkaline fuel cell, we also use the alkaline ion exchange membrane. So it contributes there.
Okay, sir. So moving to the next question. This is from again Dr. Lokesh. What is the cost comparison of CSIR-CSMCRI with MilliQ?
Our system, the manufacturing cost is around 90,000, whereas MilliQ is around 18 lakh.
Okay, sir. So moving to the next question. This is from Dr. Davis Roy. Can these membranes be used for desalination of seawater?
Yes, we are using these membranes for seawater desalination. In fact, I saw a plant which we installed in nearby Blaze. The TDS of water is equivalent to the seawater. Actually, the Blaze is on the sea coast.
Okay, sir. Thank you so much, sir, for such an interesting and informative session. This was a very interesting topic. I hope most of the participants have noted the important aspects of it. Moving the session ahead, I would like to invite Dr. Lokesh Gambhir for vote of thanks.
Thank you, Dr. Neha. Very good afternoon to everyone, and a very happy new year to all. In continuation of our efforts to bring eminence on a reachable platform, today lecture 3 under the Aegis of our lecture series 2021-22 was organized with our keynote speaker, Dr. Vaibhav Kulshrestha, Principal Scientist, Membrane Science and Separation Technology Division, CSIR Central Salt and Marine Chemical Research Institute. Sir, let me be the first one to congratulate you on your wonderful work and an insightful session. I personally enjoyed it to the most. And especially the answer that 90,000 comparing to 18 lakh, it opened my eye actually. So,
Yes.
Is there by any chance can we collaborate in terms of installing it in our lab since you hold the patent?
Yes. One can do that.
Yeah,
absolutely no problem.
Yeah, because MilliQ system purchasing is a separate thing, and then maintaining it for a longer duration of time is again.
It's very difficult. I know that. We are also having a MilliQ system.
Okay, sir. Thank you so much. So I extend my humble gratitude and heartfelt thanks to Dr. Vaibhav for taking out time to provide an insightful deliberation. Special mention to our sponsor, Soft Material Research Society, Jaipur. Humble thanks to the Honorable Management, Suresh Kanda University, for continuous support. The conveners, Professor Gaurav Sharma, Professor Ankur Jain, and the moderator, Dr. Neha Kapoor, for smooth connection of the session. And a warm wishes and special thanks to all the participants and the eminent personalities. I can see the collection of highest intellect, Professor Avasti, Professor Balram, Dr. Devesh Ray from Bhavnagar Research Center, Dr. Naveen. Thank you so much for roping in and making this session a wonderful success. Last and not the least, to all the participants, we promise you to be back in the coming week with the lecture 4. With this, thank you so much for all the participants and enthusiasm of learning and knowledge exchange. Dr. Neha, you may proceed the session ahead.
Thank you so much, sir. Thank you once again, Dr. Vaibhav, for such a wonderful session. And the feedback, there is an announcement for all the participants that the feedback link for the session would be shared via email. We'll be mailing you. That is all for today. Thank you so much, everyone, for joining. Thank you once again, Dr. Vaibhav.
Thank you very much, Dr. Kapoor.
Thank you, and have a nice day.
Thank you.